Okay, it's the year 2024, but I'm going to look at an exam question from the year 2011. If you're watching this in the future, you may not have even been born in 2011, but the diagram below shows a rhombus spanned by the two vectors a and b, and which one of these is true? It follows that. Well, if a dot b was 0, that would mean that these two vectors would be perpendicular. 90 degrees. They don't look perpendicular. They don't have to be perpendicular. I mean, we're told this is a rhombus. Like, it's not a rectangle. A equals B. A rhombus is a four-sided shape with four equal length sides. Okay, so, well, you might think then A is equal to B, but we can say the length of A is equal to the length of B. But that does not mean that vector A is equal to vector B. In fact, from the direction here, like from the diagram, clearly A is not equal to B in terms of a vector because they're not parallel. So, no. C, we've got this dot product between A plus B and A minus B. We'll come back to that one. D, the length of A plus B is equal to the length of A minus B. If we visualize A plus B is going to be this diagonal here, okay, because A plus B, and A minus B is actually going to be the other diagonal. Okay, this is going to be A minus B. This is A plus B. Because this is A here, minus B. So this is A minus B. Those lengths don't look equal. Again, unless this is a rectangle, those lengths are not going to be equal. So that's not. And 2A plus 2B is equal to 0. I mean, that is even further from the truth. If we were to do 2A plus 2B, will be double here. Would be like all the way over here somewhere. Clearly, we're not back to where we started. So by process of elimination, C is the correct option. The reason why it's correct is if we expand these brackets, this is like a difference of squares. We'll get A dot A minus B dot B. When we have a vector dot product with itself, we get the length of that vector squared. Imagine if A is like 3i plus 4j, and you were to dot that with itself, what would happen? You would get 3 squared plus 4 squared, which is the length of that vector squared. Someone's crying outside. I'm not sure how much you can hear that in the video, but hopefully not too much. Okay, so here, this is going to be 0 because length of A is equal to length of B. This is a rhombus. Okay, we said it's got 4 equal sides. This property that A dot A is equal to the length of A squared comes in quite handy in a lot of geometric vector proofs. Okay, let's have a look at the next question. Consider the 4 vectors. Which one of the following is linearly dependent set of vectors? So for linear dependence, if we have 3 vectors, if one vector can be written as a linear multiple of the other 2. We've got different options here, so I'm going to go the long way around first, and there is a shortcut to this later. I'm going to use the CAS calculator first and basically set up an equation to solve to check if A, B, and C are... Alright, so A is going to be 0i, 1j, 3k. B is going to be 1, 0, negative 4. C is going to be 0, 3, negative 1. 0, 3, negative 1. And D, 0, 2, 1. Check, of course, I have typed them in correctly. I think they are right. All right, so now we want to solve this equation. Ma plus nb is equal to c. Now, if that has a solution, then a, b, c must be linearly dependent. So m times a plus n times b, we'll need the times signs. For m and n, no, it does not work. Okay, so now once we've defined the vectors, the rest should be pretty quick, like checking a, c, and d. Well, change the b to a d, then I've got a, c, and d. There we go. So that does have a solution. The answer here should be B. All right, so the clever way to actually realize that A, C, and D are linearly dependent is to notice that B, A, C, and D only have J and k components. Whereas vector B has an I component. A, C, and D only have J and K components, meaning that they're actually in the, they're all in the YZ plane. Whereas vector B, which has an I component and a K component, is going to be in the XZ plane. It's a little bit hard to draw planes on a 2D axis, but let me try. So this is going to be the YZ plane, parallel to the Y and Z axis, something like that. Okay, vectors A, C, and D are all in there. Vector B is not. If they're in the same plane, they're linearly dependent. Okay, let's have a look at one more. The angle between the vectors A and B is best represented by, okay, so definitely the best approach to this one to be to get out the CAS calculator and then sort of calculate, because we're going to use the dot product. So if we can calculate A dot B over length of A times length of B, that will give us the cosine of theta. Again, define the two vectors. A is going to be 1, negative 2, negative 2. B is going to be 2, 1, 2. And then we want the dot product of A and B divided by the length of A times the length of B. Dot product, just dot P. You could also find it under the CAS menu, matrix, and vector. You got to go down to vector, dot product. To do the length on the CAS, we use the norm function. So norm of a vector is the length of vector. Again, we can just type NORM, but it is under the matrix and vector norms there. Okay, we don't want norm, we just want norm A times norm B. Okay, that gives us negative 4 over 9. So this is telling us the cosine of theta is equal to negative 4 over 9. So what does that tell us about the angle between the vectors? Well, it should be the inverse cosine of negative 4 over 9. But that's actually not one of our options. So, I mean, we could like get this on the calculator, check through all of these to see which one it's equivalent to. But let's see why it's going to be this one here. The cosine of theta is negative 4 on 9. So if the cosine is negative, think about the unit circle. We're in quadrant 2 or 3. So let's say if we're in the unit circle, negative 4/9 is just about like less than half. What are the two vectors going to look like? Well, so our angle is, you know, going around to say here. We want the angle between the two vectors. And what we know is that the cosine is negative 4 over 9, like just to here, right? Well, the inverse cosine of 4/9 would be like this acute angle in here. If that were in Q1, that'd be inverse cosine of 4/9. We want this obtuse angle, so we want 180 minus the inverse cosine of 4/9. Okay, in radians is going to be pi minus the inverse cosine of 4/9. Again, if you're not sure about the geometric interpretation, like you could just, you know, bash this into the calculator. Inverse cosine 4/9, and then check that when we do pi minus the inverse cosine of that, we get the same, negative. So if we put inverse cosine of negative 4/9, and okay, so we get the same thing. All right, that's it for now.